Okay, everyone. Well, that was quite a journey in our chapter 2 so far, from metric spaces and convergence over normed spaces. Look at these unit circles here. Lots of different sequence spaces, and then Banach spaces. Whole lot of examples here. Okay, up until we reached Hilbert spaces, which in some sense is the non plus ultra in our family or hierarchy of different kinds of spaces that you can see here. Okay, and then we got at least an idea of what you can do if you have a Hilbert space with all its features. Now, if you're asking what's next, then the next thing is going to be linear operators. So we will look at linear operators between these kinds of spaces, and the more features your space has, the more kinds of features of operators you can study. And this is still chapter 2 because it's still crash course in functional analysis, but we are on a good way to making our way through the chapter 2, so stay focused. Our first topic in section 2.5 is bounded linear operators. And before we can talk about what bounded linear operators means, we have to explain what a bounded set is. And to do so, let's get back to the very basic case of a metric space. Which of course covers all the other cases like normed spaces and Euclidean spaces, Banach spaces, Hilbert spaces, and all the rest. And let's say that a subset S of x is called a bounded set if there exists a real number, let's call it d, greater than or equal to 0, such that for all points or vectors x and y in our set S, it holds that the distance between x and y is less than or equal to d. It's easy to conceive what that means. If this is your metric space X, and there is your subset S, then whatever points X and Y you choose in S, their distance from each other is never more than a certain number d, and that number d is also called the diameter of the set S. Now this definition is fairly easy to understand, but not always the easiest to use. So let's rephrase it in different ways. The following statements are equivalent. This is often abbreviated by the following are equivalent. Okay, statement 1, your set S is bounded. This is equivalent to statement 2, and here we just copy what we say in the definition. So these two are obviously equivalent by the definition of boundedness. Now here is something new. For every x in, and now this is x, not s, there exists a number, let's call it rx, and refer to it as a radius greater than or equal to 0, such that every y if s is within that radius of the point x. So the distance between x and y is bounded by this radius rx. So this means that no matter where in X you're putting your point little x, you can cover the whole set S by a circle around X with that radius little rx. And of course that circle around your point X is not ending at the corners of capital X like I was drawing here, because capital X has no boundaries like this. So it's a proper neighborhood around your point X that covers the whole of your set S. So why is that equivalent to statement 2? Well, you could first look at some point in S and then check the distance from your point X to that point S, maybe in green. Measure that distance with your distance function or matrix little d and call it maybe L, which is certainly a finite number. But then by statement 2, from that blue point to any other point in S, the distance is not more than capital D, our diameter, which of course shows that the red point is within distance less than or equal to L plus D from your point X, and that's how you're going to put your little Rx. The other direction is easier to see. If statement 3 holds, then 2 automatically holds, because your point X from statement 3 could in particular be a point of S, and then the rest of 2 just follows. Okay, and the fourth property, which is also equivalent to the other 3, is that we're not expecting for all X, but there exists an X in X, and the rest is just as in property 3. There is a radius R depending on that point X, so that every point of S is within that radius of that point X. So it's clear that property 3 implies that new property 4, because if it holds for every X, then it holds for at least one X. To see the other direction, let's argue that the new property 4 implies the property 2, which we already know is equivalent to 1 and 3. And to see that, let's assume property 4 holds, and then, as in property 2, let's take any 2 points X and Y in S, maybe here and here, and let's show that the distance between the red point and the blue point is less than or equal to some d that we can pick. And we're going to pick it as follows. Well, by triangle inequality in that triangle here, we know that these two lines are in length less than or equal to r of x, because we have property 4. So we conclude that the distance from red to blue is by triangle inequality less than or equal to r of x plus r of x, which is what we're going to call our diameter d, and there we are. Here's property 2. So if someone asks you what is a bounded set, then you could say, well, it's a set where any 2 points in that set have distance from each other not more than a certain number d that we call the diameter of S. Or you could say a bounded set is a set that you can cover by a disk, and the center could be at a particular point, it could be at any point, doesn't make a difference. Right, now that we got this covered, we can start talking about bounded linear operators. So what is a bounded linear operator? a linear operator A from x to y. I'm going to say in a minute what x and y have to be, is called bounded. So it's bounded linear operator if it maps bounded sets of x to bounded sets of y. So here's the notion of a bounded set that we defined before. So x and y should at least have a metric, so we can speak about bounded sets. On the other hand, x and y should have addition and multiplication by scalars, so we can speak about linear operators. So they have to be vector spaces, and they have to have a metric each. So let's take normed spaces, which covers it both, right? So let these be normed spaces, which guarantees both the existence of addition alpha times, but also the notion of a metric via a norm.